Hello students. Uh, in this lecture, I'm going to discuss some of the basic results of the Strum theory, and from now onwards we write the self-adjoint second order equation in the form d by dt into capital Pt dx by dt plus qt x is equal to 0, where capital P has a continuous derivative, Q is continuous, and capital PT is taken to be positive on the given interval AB. So let's start the basic results of the Strum theory. Our first result on the Strum theory is based on the theorem named as Bolzano-Weierstrass Theorem. The theorem states that every infinite set which is bounded will have at least one limit point, and we will use this fact in proving the next theorem. The theorem is, let f be a solution of the second order homogeneous self-adjoint equation d by dt capital Pt dx by dt plus capital Qt x is equal to 0. This function f, which is solution of the given differential equation, must have first derivative f dash on the given interval ab. And we also suppose that the function f has an infinite number of zeros on the given interval ab. That is, there are infinitely many points, say t1, t2, tn, and so on, for which fti is equal to 0. That is, ft1 is equal to 0, ft2 is equal to 0, ft3 is equal to 0, and so on. So we have a sequence, infinite sequence of zeros of f. And in the theorem, we want to prove that if f is such a set having infinite number of zeros and is also a solution of the second order homogeneous linear self-adjoint equation, then the function itself is 0. So in the proof, we will use two already known theorems. First one I have already stated, namely Bolzano-Weierstrass Theorem. And the second result which we use is the corollary to theorem number 1 of nth order homogeneous linear differential equation. So please also read that statement, because that is useful in proving the result. So now let us start the proof. Now since f has infinite number of zeros, so the set of zeros has a limit point, say t0, using Bolzano-Weierstrass theorem, because we have given that the first derivative exists. That means the function is continuous on the closed interval ab, because we know that every continuous function on a closed interval is bounded. Therefore, the set of zeros is a bounded set, and hence we can use Bolzano-Weierstrass theorem, and this implies there exists a t0, and which is a limit point of this set of zeros. Again, using the fact that f is continuous, we can write limit t approaches t0 ft as ft0. Now, if we approach t naught through the zeros of the functions, say tn's, then we get that limit t approaches t naught ft must be 0, because the points t are now the zeros of f. We are taking a special route to approach t naught. Which route? Which path? We are taking the path passing through the zeros of f, and therefore the values of t will be the zeros of f, and hence when you approach t naught through these zeros of ft, you will get that limit is equal to 0. But we have already know that since function is continuous, this limit must be f of t naught. So we get that the value of f of t naught is 0. Now again we write the f dash t naught in term of the definition of the derivative. In term of definition, f dash t naught is equal to limit t approaches t naught ft minus ft naught over t minus t naught. Now, if you observe this function ft minus ft naught over t minus t naught is equal to 0 when you approach tn through the zeros of ft. So, f dash t naught is always 0 because ft is 0. ft naught, you have proved that ft naught is 0, so numerator ft minus ft naught is 0 because the points t are now the zeros of f. So ftns is equal to 0 when you approach t naught through tns. So we have a function f which is a solution of the second order equation and having the property that at some point t naught ft naught is 0 and f dash t naught is equal to 0. So now we can use corollary to theorem 1 of the nth order homogeneous linear differential equation, which says that if there is a solution of this equation having these properties that ft naught is equal to 0, f dash t naught is equal to 0, then f itself is 0, which proves the theorem. And now in theorem 22, we will prove Abel's formula. Abel's formula for the Strum theory states that if f and g are any two solutions of the given self-adjoint equation on the given interval ab, then for every point t in the given interval, the function capital Pt into ft g dash t minus f dash t gt becomes a constant. So let's see the proof. Since f and g are solutions of the given self-adjoint equation, so we can replace x by f and x by g. So replacing x by f and g, we get the equations 1 and 2. So from equation, if we multiply equation 1 with g dash with minus gt and equation 2 by ft, and if we add both the equations, we get that small ft d by dt into capital Pt g dash t minus gt d by dt capital Pt f dash t is equal to 0, because the second terms of the equations 1 and 2 got cancelled when you multiply equation 1 with minus gt and 2 by ft and add. Now integrate this new equation from a to t, and when you integrate, you see that integral becomes fs capital Ps g dash s from a to t minus integral a to t capital Ps g dash s f dash x ds minus gs capital Ps f dash s from a to t plus integral a to t capital Ps f dash s g dash s ds is equal to 0, and we obtain this using integration by parts. So when you integrate by parts, and you can observe that this integral terms, namely minus integral a to t p capital Ps g dash s f dash x ds and the term integral a to t capital Ps f dash s g dash s ds, they got cancelled, and thus we have left with two terms, and from which we can take the term capital Pt as common. So taking the term capital taking the term capital Pt common, and in the left side we are taking the terms involving t only, and in the right hand side we are taking terms after substituting the lower limit, namely a. So we get that capital Pt ft g dash t minus f dash t into gt is equal to capital Pa into fa g dash a minus f dash a ga. But you can see that the right hand side term is evaluated at a, so it must be a constant k. This completes the proof. We wanted to prove that capital Pt ft g dash t minus f dash t gt is equal to constant, and that constant we have evaluated, and that constant is capital Pa into small fa g dash a minus small f dash a ga. So let's start our next result. In our next result, we will prove that if any two solutions of a self-adjoint equation have a common zero on a given interval, then both the solutions must be linearly dependent. So we have given that the functions f and g are solutions of the self-adjoint equation given by 1. Here these two solutions f and g have a common zero, that is there exists a point t in the given interval ab where ft is equal to 0 and gt is equal to 0. Then we have to prove that these two functions f and g are linearly dependent on the given interval. So let's start the proof. Since f and g are two solutions, and we have already proved the Abel's formula for the two solutions, which states that capital Pt into small ft g dash t minus small f dash t gt must be a constant, and we have given that the functions f and g have a common zero. So we are taking that common zero as t naught. It means that f at t naught is equal to 0 and g at t naught is equal to 0. So if we evaluate the equation 2 which we got from the Abel's formula, if we evaluate this equation at t naught, then we get that pt naught into ft naught g dash t naught minus f dash t naught gt naught is equal to k. But since ft naught and gt naught are 0, so left hand side of equation 2 becomes 0, and this implies k is equal to 0. Now we have already mentioned in the starting of my lecture that the equation we are considering is a self-adjoint equation, and here we are taking capital Pt as a positive function. So we are now using that property here. Now since capital Pt is positive, so this implies that this function ft g dash t minus f dash t gt must be 0 because k is 0. So either pt 0 or this ft g dash t minus f dash t gt is 0. But since pt is greater than 0, so this implies the second term in the equation 2 is 0 because k is 0. So if we write second term in the form of a determinant, we get that this is nothing but the Wronskian of f and g. So and we are getting that this Wronskian of f and g is 0 for all t in AB. But we have already proved that if Wronskian of two functions is 0 for every point in the given interval, then it means that they are dependent on AB. And this completes the proof of the theorem number 23. In our next theorem, we will prove the converse of theorem number 23 by taking f and g as non-trivial, linearly dependent solutions. So, the statement of theorem 24 is that suppose you have given f and g as non-trivial, linearly dependent solution of the equation 1. And suppose that there is a point t naught in the given interval where f is 0, that is t naught is a 0 of f. Then we will prove that this t naught is also a 0 of g, that is given any non-trivial linearly dependent solution of the self-adjoint equation 1, then both the solutions have a common 0. So let's start the proof of the theorem. Now, since we have given that f and g are linearly dependent, so we can find constants c1 and c2 not both 0, such that c1 ft plus c2 gt is equal to 0 for every t in the interval ab. And we mark this equation as equation number 2. Now, since f and g are both non-trivial solutions, this implies that neither f and nor g is 0 for all t on AB. Now, if C1 is equal to 0, then from 2 we have C2 into GT is equal to 0 for all t in AB. But because GT is non-trivial, so there must exist some some value of t for which gt is not equal to 0, and for that we get that c2 is equal to 0. And this is a contradiction because we have already taken that c1 is equal to 0, and since f and g are are linearly dependent, so these constants c1 and c2 both cannot be 0 together. So now similarly, if c2 is equal to 0, then again from 2 we can find that c1 is also 0. So this is again a contradiction. This implies that neither c1 nor c2 in equation number 2 is 0. So now we have also given that t naught is a 0 of the function f. So when we substitute t is equal to t naught in equation number 2, we get c1 f t naught plus c2 g t naught is equal to 0. But because f t naught is equal to 0, so we left with c2 g t naught is equal to 0. But because we have already proved that neither c1 nor c2 is 0, so this implies that g at t naught is equal to 0, and this implies that t naught is also a 0 of g, and hence the theorem. Our next result is term separation theorem, and it separates the zeros of the two solutions which are given to be linearly independent. So let's start the statement. Now let f and g be real linearly independent solutions of the second order self-adjoint equation d by dt pt dx by dt plus qtx is equal to 0. Now we want to prove that between any two consecutive zeros of f there is precisely one zero of g. That means if there are two points t1 and t2 in the given interval AB such that ft1 is equal to 0, ft2 is equal to 0, and in between t1 and t2 there is no other t for which ft is equal to 0, then there exists one and only one point in between t1 and t2 where the function g is 0. So that means for the two linearly independent solutions f and g between any two consecutive zeros of f, there is exactly one zero of g. So let's start the proof. Let t1 and t2 be two consecutive zeros of f on the given interval ab. Then gt1 is not equal to 0 and gt2 is also not equal to 0, because we have already proved in our previous theorem that if they have both the functions have the common zeros, then they must be linearly dependent, and it means that our given solutions f and g are linearly independent. So it means that both the function cannot have the common zeros. So if t1 and t2 are zeros of f, then t1 and t2 cannot be zeros of g. So at the point t1, gt1 is not equal to 0 and t2, gt2 is not equal to 0. Now, we want to prove that there exists exactly one zero of g in between t1 and t2. So we assume contrarily that suppose there exists no zero in between t1 and t2. No zero of g in between t1 and t2. That means g is never 0 in the interval t1 and t2. Both the functions f and g are twice differentiable. It is already given because we have given that they are solutions. Solutions means solution of second order differential equation. It means they satisfy, and they satisfy means that their second order derivative should exist. So f and g are twice differentiable and both have continuous derivatives on closed interval ab. So this implies that the function f by g has continuous derivative on the interval t1 and t1 to t2. Also, if we evaluate the function f by g at t1 and f by g at t2, because numerator is ft1 which is equal to 0 and ft2 which is equal to 0, therefore the function f by g at t1 and at t2, at both the points t1 and t2, the function f by g is 0. So if we collect all these hypotheses that f by g has continuous derivative on the closed interval and at the endpoints the function f by g is 0, so all the hypotheses of the Rolle's theorem are satisfied, and therefore there exists a point xi in between the open interval t1 and t2 where the derivative of this function f by g is 0. That means d by dt of f by g at t is equal to xi is 0. Now, but d by dt of f by g is Wronskian of the function g and f over gt square. But we have given that f and g are linearly independent, and therefore this Wronskian of g and f is never 0. It means that d by dt of f by g is not equal to 0 in between t1 and t2. So in between any point t1 and t2. So this is a contradiction because we are already proved by the Rolle's theorem that there must exist a point zeta in between t1 and t2 where the function's derivative is 0. But when we are evaluating the derivative, the numerator term is Wronskian of the function g and f. But because the functions are linearly independent and their Wronskian is never 0, and therefore we are getting a contradiction. This contradiction arises because in the starting of the proof, we have assumed that G has no zero in the interval T1 to T2. So, there G has a zero, at least one zero in interval T1 to T2. Now, remaining to prove that G has exactly one zero, because we want to prove that between any consecutive zeros of F, there exists one and only one zero of G. So uniqueness has remained to be proved. So suppose G has more than one zero in the given interval, and name those zeros as T3 and T4, and take them to be the successive zeros of G. By successive or consecutive zeros of G or F, we mean that in between those two zeros, there does not exist any zero of the function. Now, if in the above proof we interchange the role of F by G, we will get that between T3 and T4, there is at least one zero of F. That means what we have already proved above, we are just interchanging the role of F by G. In the proof, we proved that if T1 and T2 are two zeros of F, we have already proved that there exists at least one zero of G in between T1 and T2. Now we are given that there exist two zeros of G, T3 and T4, and when we interchange the role of F and G, we get that there exists at least one zero of F in between T3 and T4. So if we arrange the interval, and if we arrange these zeros as the points on the interval, then we get that T1 is less than T3 and T3 is less than T5, T5 is less than T4, T4 is less than T2. Here you can notice that T1, T2, T5 are zeros of F. But as we know that T1 and T2 are two consecutive zeros of F, so in between T1 and T2 there cannot exist a zero of F. So, but here we have proved that if G have more than one zero, then there exists a zero T5 of F, which is a contradiction. This implies that G has exactly one zero in the given interval T1 and T2, and this completes the proof.